Okay, this is Cullen Joyce, and this is my winter culminating project. I hope you enjoy it, and let's get started. Okay, so I'm going to be talking about the transesterification reaction as well as biofuels. Okay, so the process of transesterification, this is where triglycerides or fats or oils react with an alcohol group. This is probably the most relatable thing you can talk about in quarantine and college because everyone has gotten a little bit fat in quarantine, so we could use those fats and mix them with alcohol, which people have been using a lot during quarantine. So the structure of the molecules we're going to use in this reaction are fatty acids, which are what they store energy in the human body for long term. That's where they store them. And this is what they look like. So you have a long hydrocarbon chain here. That's all the carbons there. And then you have this, there's a hydrocarbon chain, and the carboxyl group right here, as well as the hydroxyl group on the end there, which is included in the carboxyl group. And then we have esters, which have a similar hydrocarbon chain, the same, it can vary depending on the fatty acid. We have that hydroxyl group, which is replaced with the alkoxyl group. So the hydrogen's gone off and we include a methyl group in there. So the triglycerides, and this is what they look like. I'm just gonna move my face out of the way. So we have the similar fatty acid, we have 3 fatty acids lined up here. That's what the squiggly lines are. Those are the hydrocarbon chains. So that's still the same. We have the double bonded oxygen, and the methyl group has turned into a glycerol backbone there. So they're all connected by the glycerol backbone. That is what makes the triglyceride. That's how they store fatty acids in the human body. Okay, so what structures equal what properties? So it's usually the functional groups that determine the properties of a molecule. So we're going to talk about the hydrocarbon chain, which doesn't really change throughout this reaction. It stays pretty stationary. This is what it looks like. Also the squiggly lines in some of my drawings. As you can see, it's saturated with all those hydrogens, not really looking to change too much. All those molecules are pretty happy. And then we have the carboxyl group. So this is a big factor in the reaction because you can see there's a double bond there, which is oxygen is super electronegative. So it's always happy to take that pi bond, take the electrons from that. So that gets things going. And there's also a high electron density over here because you've got the hydroxyl group and the double bonded oxygen there in the carboxyl group. So there's just a lot of electrons clumped at the end there, and you'll see that this is what causes the reaction to go forward as nucleophiles because they're willing to give away those electrons. As well as the hydroxyl group, which is on the carboxyl group there, but I just added another picture here so you can see there's the oxygen and the hydrogen added there. So oxygen's super electronegative, so it pulls the electrons closer to it. Hydrogen, not that electronegative, so it's willing to go be an electrophile and accept electrons, and the oxygen will break that bond and take the electrons as the nucleophile. And then the alkyl groups, which we have already discussed with the stuff, glycerol backbones, which is also pretty sturdy apart from the hydroxyl groups on it, but you'll see it stays pretty much the same throughout the reaction. So we start with triglycerides. I already showed you guys this. Alcohol, that's our methanol right there. So you get the methyl group and the hydroxyl, as well as the catalyst, which is sodium hydroxide right there. What we finish with, we're going to finish with glycerol, which if you turn the triglyceride molecule, if you turn that sideways, you'll see that it fits right on there. We just take these hydroxyl groups off the end, just take hydrogens off, and it bonds to it. Methyl esters, which are these right here, also known as biodiesel. So that is the main focus of this reaction. So those are monoalkyl esters, but you can also have more than just monoalkyls. You can have more, but we are reacting methanol, so we're just going to get the monoalkyls. As well as the catalyst, which is sodium hydroxide, which I already spoke about. And then we are going to go to the mechanism of the reaction right here.
I'm going to be explaining the mechanism behind transesterification. I've done some good housekeeping by already drawing out all the molecules in an easily usable form. Now I'm just going to draw any electrons as well as the mechanism. Okay, so our starting products, we have alcohol and triglycerides. And then our final products, we have glycerol and methyl esters. Okay, so the catalyst that helps them get there is sodium hydroxide. So let's get started. Let me draw that. So if you look at the polarity here, you have positive here. This oxygen is going to be negative. This bond in between the hydrogen and the oxygen is going to break. This oxygen is going to uptake those electrons. And then this oxygen is going to take that hydrogen right there. So draw that there. So that is going to create H2O as well as methyl oxide. So I'm going to draw in a methyl oxide right here. So we have our methyl group right here. And then we have the oxygen with 6 electrons now. So it's a very negative charge. And then we've got our triglyceride molecule right here. As you can see, it's 3 fatty acids connected by glycerol backbone. The only thing you're missing from this glycerol here is those 3 hydroxyl groups. So just have you note that. And then these fatty acid chains, these lines are just hydrocarbon chains. They can be shorter or longer. It's all dependent on the fatty acid that you have. So this methyl oxide is going to react these carbons right here. Carbons are going to act as electrophiles. So they are going to accept these electrons right here. The ratio of alcohol to triglycerides is 3:1. So there's going to be 3 methyl oxides for every 1 triglyceride. That's what's needed to make the reaction go towards the right. But they usually do 6:1, like the Chatelier's principle, to push it further. So there's going to be 6 to every one of these. See, so I'm just going to draw this happening 3 times. 1, 2, 3 instead of drawing that time. Okay. So as you can see, there's an intermediate stage. It's not going to go exactly to glycerol and methyl esters. So that's what I'll take you through right over here. So we have the intermediate stage. We have the methanol reacting with the sodium hydroxide, giving us the methyl oxide and H2O. So the methyl oxide has reacted, the oxygen has reacted with that carbon there. There you go. And then it's going to give you this intermediate structure. I just drew the triglyceride as 1/3. It's the glycerin backbone as a word here, it's connecting it, just because it's a lot more. But here you go, you're going to have this carbon connected to 3 separate oxygens. This pi bond is broken, so this oxygen uptook those electrons. Pi bond broken, you have single bonds all around here. So this guy is going to have 6 electrons. This guy's. Okay, so this guy's not very happy because he lost his pi bond. He wants that back, so what he's going to do is he's going to throw those electrons back on top of that single bond, creating a pi bond. As you can see down here, he got his pi bond back, but at the cost of this guy's bond breaking. So he's going to uptake those electrons. This bond is broken right here, and that's how you get the glycerol backbone breaking away from the triglycerides. And as you can see, you're left with 3 fatty acids, even though it's separate. So you come down here, this methyl group right here, or methyl oxide group, goes down, and you just have to. Okay, so here. So the glycerol is still not complete. We have the propane chain right here, and then you just have the oxygens sitting on the outside here. So these are still extremely electronegative. They're going to have 6 electrons on the outside of them, right there. So these are all negative. And they're going to be the nucleophiles in this case. What's going to accept the electrons is going to be one of the hydrogens off the oxygen here. So we're going to draw these in here. We're going to start the electrons, draw them off that hydrogen there. So we're going to do that 3 times. So this oxygen bond will be broken. This oxygen is going to accept those electrons on all 3 of the waters. And then you're going to have your glycerol being completed with these hydroxyl groups right here because they got those hydrogens there. Okay, So that is the catalyst, sodium hydroxide, is going to be reformed, and that can be collected. And then we have our glycerol, which has been completed, very dense molecule, so that's going to sit at the bottom of the barrel or whatever you're forming this in. And then we are left with our methyl esters here, just 3 fatty acids here. You got your carboxyl groups on the end here, our little methyl groups added, and your 2 fatty acid chains. And those methyl esters are actually called biofuel, and that's what you're going to put in your car so you make it run. And that is less dense than the glycerol, so that's going to sit on top. So they put a spout at the bottom, they funnel the titration out, and you're just left with methyl esters, which will in turn drive the reaction further to the right, because that is, yeah.
Thanks, Colin. Couldn't have said that any better myself. Okay, so we're going to talk about why this reaction happens. We're going to talk about the small scale, the nature of the reaction, not the things that are controlled. So this is due to the functional groups and mostly the electronegativity that is caused from the carboxyl group as well as the hydroxyl group. And that is because there's so much electron density at the end of those fatty acids and at the end of those hydrocarbon chains. So that's what really causes the reaction to go forwards. And you see that on the triglycerides and the fatty acids because, I mean, they both contain each other. The long carbon chain isn't really what causes this. You'll see that stays the same throughout. Yeah. And then this is why the reaction happens on a large scale. And this is more the nurture of the reaction. This is what factories can control. And this is how they push the reaction forwards to get more of what they want out of the reaction. So they use Le Chatelier's principle, which works because this is an equilibrium reaction. So they increase the concentration of the reactants, which will move the reaction towards the right and will create more products. So the ratio that's needed is 3 to 1. Actually, we'll do 3 on this side, 3 to 1. So what they do is they increase the product, so they'll go 6 to 1, and that drives it further towards the products because there's an increased concentration on this side, as well as the catalyst NaOH, which helps drive it forwards. So they also do the reaction 2 times just to make sure that it's gone through completely and all the products have moved, as well as at the second time they drain the glycerol from it, which removes some of the products, which will decrease the concentration over here, moving that gradient towards the right again, towards the product. So why do we care about this reaction? I know I've been going off about it. It's actually a really important reaction. And I'm going to tell you why. It's because of the substance that it makes, these methyl esters. It takes everyday waste products like food oil that we use, cook our bacon in. We could use bacon grease. We can use olive oil. We can use things that we've already used that we usually just throw out, and we can turn it into a fuel. More specifically, a biofuel. And like we have fuels, and I know that's not that crazy, but this is a renewable fuel that we can use in the same engines that we're using the fossil fuels in. So we can use it to power everyday things. We don't need these weird new inventions. We can use the same inventions and power it with vegetable oils or animal fats. Like we could use this on cars, heating houses, creating electricity, which in turn you can use to power your phone and make this presentation on my laptop that I'm making right now. You can even use it to fuel your spaceship. I know I'm getting a little carried away on that one. That's a little too much potential, but the potential is unlimited here. So it's taking everyday waste, turning it into fuel. That's coming from animals and vegetable oils, more specifically the fats within them, the fatty acids, which are stored as triglycerides in human bodies for long-term storage. So it makes sense if you think about the human body as an engine, it makes sense that we can use the fuel for the human body on different engines. And in fact, the first diesel engine was designed and used vegetable oil to run, but due to complications with weather, like when it was cold out, the vegetable oil would, like saturated fats, it would clog up. So they turned to petroleum oil because it didn't clog up at colder weathers. But what they've done to overcome this is you do a mixture of biofuel and diesel, regular petroleum diesel, And it still works. They can work together in harmony, and you just get a mixture going in, and they'll burn the same way. It's renewable, like I said. Vegetable oil and animal fats are regrowable. We can regrow the vegetables that we're using to make those oils. We can have more animals. So this is a renewable energy source. And it can also be locally sourced. And what I mean by that is that we can make this stuff in our Queen's chemistry labs. So we could have like a local economy about this type of fuel. We don't need to ship it from another country or somewhere else. We can just make this fuel ourselves and be using what we are creating. So as you can tell, I'm really excited about this because this is the way of the future, and you can see more biodiesels being created and added to everyday fuels. And even at gas stations, you're seeing more of these options where it is more of a biofuel mixture. So with that, that concludes my CHEM Culminating project. Thank you. And I will see you guys once you correct this, I guess.